And welcome back for another edition of the Syzygy podcast, everyone's favourite astronomical podcast. Joining me at the microphone, as ever, is Emily Brunsdon.
Hello, hello.
So, Emily, this time we're going to talk about the origins of the solar system, where we look up into the night sky, and one of the things that astronomers are really keen to do is to figure out, where does all of that stuff come from? How did it get to be the way it was? The stuff which is closest to home, the 8 planets, the moons, the asteroid belt, all the stuff that's around us in the solar system, it's very easy to kind of take it for granted. Well, we know where all of that's from. We know where it is and we know what it's doing. But it's actually a little bit more complicated than that. So we're going to talk about that today, the origins of the solar system. How do we start this one?
Yeah, well, we can know that our solar system's kind of 5 billion years old. And that's not necessarily a problem. That's a long time, right? We're not going to see solar systems evolving live in front of us.
No, it's going to take a long time.
It's going to take a long time. But that's not necessarily a problem. We're quite used to things taking a while in astronomy. But what we've always been really excited to do with that kind of system where you have to wait a long time is that, well, we can go out in the universe and find lots of examples that are at lots of different points along their evolution and to go and to see what and join the dots up between them.
It is one of the things that I do love about reading about and listening to astronomers talk is this sense of what constitutes a long and a short time in astronomy. You know, astronomical timescales, a couple of billion years, that's nothing. That's nothing. So the point that you were just making about being able to look out into the universe and see different examples, we can see now systems around other stars of planetary systems at different stages of evolution, presumably from the very, very early right through to the very, very old.
Well, actually, that's not quite the case. Most of the time when we're looking at planetary systems, exoplanetary systems, they're formed, right? The planets are there, they're going around their host star, and many of them are as old, if not even older, than our own solar system. But we do have other examples in astronomy where we've done this very successfully. I mean, let's take the evolution of a star.
Okay.
We can go and see a star being born in some places in the galaxy. We can see young stars that are in kind of the middle ages of their life cycles, and towards the end, and all the wonderful things that happen to stars when they end their lives. We've seen examples of all of those things, and we can sort of join those together and say, well, okay, that's an evolutionary sequence.
So even though you can't see a specific star going through its entire life cycle, you can add up all the pieces from observing very, very young stars right at their birth, right through to the end of life in all the different ways that different stars can do that. And you can put that together as a sequence. So presumably you can do the same sort of thing with planetary and solar system type evolution.
Well, it becomes a lot harder because it turns out that the process when the star is being born and it's forming the planets kind of at the same time, that's in a place in the universe that's very, very hard to access, which is deep down inside what we call giant molecular clouds. And these are by nature dark and quite cool, so we don't have very good probes to sort of see deep down inside of these clouds to sort of and see what's going on.
That does make it a little bit difficult.
That makes it really tricky.
Okay, so what do you do?
So, well, we have one example of a really good solar system that we know very well what's in it, at least in the inner and the edges of the planets in our solar system. It's very mysterious kind of what happens out in the Oort cloud, as we discussed a few episodes ago. But we have some pretty good data from our own solar system. And then what we're able to do now, which we were never able to do before, is say, well, okay, we've got one solar system, but now we've got other exoplanet systems. So we can say, well, is our solar system normal? Is it different to all the others? But we've got lots now of examples of these kind of endpoints, or at least middle ages of solar systems.
So we have all of this, as you said, we've got all of this data from our own solar system. But of course, we can't see our solar system back in time. We can't see back to the beginnings of our own solar system. So how do we know? How do we know about the earliest stages? How do we know where our solar system came from?
Okay, so we know where we've got to get to,
Yeah.
right? We've got to get to the point where we are now. We've got a sun, we've got 4 rocky planets, we've got an asteroid belt, and then we've got 4 gas giants.
So we've got the end point. We've
Yeah.
got that end of the boundary conditions, if you like.
Yep.
How do you get there?
So you've got to start with, okay, you've got to get to there, and you know some things about what the properties of the things in the solar system are. All of our planets, for example, go around the sun in the same way, in the same direction, and they're all pretty much in circular orbits. And for the most part, they also rotate in the same direction.
So give or take a few anomalies there, everything's behaving in pretty much the same kind of way. So what does that tell us?
Well, that doesn't happen just randomly.
Right.
So we think that means that they all formed kind of in the same way from the same body of material.
That makes sense. If you saw planets going around in all sorts of different directions with all different kinds of stretched out orbits, and some of them rotating this way and some of them rotating that way at all sorts of different angles, then you'd think that's pretty chaotic. They must have just sort of all clumped together in some weird way. But if they're all behaving in the same plane, going in the same direction, spinning in the same kind of way, that does kind of suggest that they have a common origin, a common past.
Yep, and they're also tied to the sun.
Right.
So they're also in the same plane of rotation as the sun's equatorial axis, so they rotate and the sun's spinning in the same way. So that now tells us that the planets are all linked, and they're also linked to the sun. So I think we have to hit rewind and go all the way back to how did the sun form.
Okay. All right. Let's start with that then.
So we have this wonderful term, I think, in astronomy, which is called, so we have stellar nurseries.
Stellar nurseries. That's so cute.
It's really cute. The stars are not very cute inside stellar nurseries.
No, I remember you saying that a podcast or two ago, that young baby stars are not adorable, cute little things, that they're violent.
Yes. So how do they get to be violent is a good question. So if you have a stellar nursery, you have a big cloud of gas and dust. And Hubble has amazing pictures of some of these examples. I think probably one of the most famous one is the Pillars of Creation.
Oh, yes. Yeah, we'll put some pictures in the show notes as ever, but this is one of the great ones.
It's got to be one of my favourite images.
Yeah, these amazing fingers that look, I mean, it doesn't look like the sort of thing you could conceive of finding in space. There's just so much structure. And tell me about that structure, because I've seen those pictures so many times, and I've heard it said about it that, okay, stars being born in here. But what are we seeing when we look at the pillars of creation?
So those pillars themselves, the structure, they're part of this giant molecular cloud. And that's a part of a big cloud of gas and dust and a lot of very cool gas, particularly that's molecular hydrogen. We've got some helium in there.
Where are they, by the way?
They're in the Eagle Nebula.
Which is where? Like, in our galaxy?
Yeah, in our galaxy. Yep. About
else?
6,500 light years away.
Okay. Eagle Nebula, Pillars of Creation, got it. And we've got, you were saying, cool gas.
Cool gas, yeah. So this is not hot. So that means that the cool gas forms molecules, which means it's kind of opaque to look through. We can't see through it, which makes it look dark in the sky.
Which is what we see when we see the structure in these things.
Yeah. And there's kind of bright light coming from behind the nebula, so it kind of shadows onto the bright light. And so in that giant molecular cloud, then little clumps of that giant molecular cloud might be a little bit denser than other clumps. It's not uniform in distribution. And over time, we expect that whole cloud to give birth to something in the order of thousands of stars from these little clumps.
Wow. So the clumping together, gravity in those clumps takes over and begins to squash them down, pull them down and create stars.
Yeah, and we suspect that maybe that kick, the initial push, if you like, that starts pushing the cloud to squeeze it together might be another supernova explosion.
I mean, because supernova, we discussed a little while ago, these are big explosions. These are shockingly big explosions. And so the shock wave, the energy burst that's coming out of one of these supernovas, rippling across through these gas clouds, could be enough to give things a bit of a nudge to start collapsing down and turning on.
Yeah, and we
so
think
the death of stars gives birth to new ones.
Yeah, it's a lovely generational thing.
Isn't it?
It is really nice. It's really nice. So probably for our solar system, a supernova went off, and we think we have some remnants actually of the material. We have some iron, for example, in our solar system, in our sun, that probably came from this supernova. So that maybe kicked off the collapse. And then once you have collapse of a cloud, it starts going into runaway collapse. And the whole thing is just under its own self-gravity, just pulling itself together faster and faster and faster.
Now, so once you've given it a bit of a nudge, then it takes off. It pulls itself by its own bootstraps, as it were, and gravity takes over and it collapses down. And eventually it gets so dense that the nuclear reactions start turning on. Nuclear fusion starts turning on.
Well, even before that happens, then you start to warm up your gas cloud, right? So it's getting warmer, and it's getting warmer and warmer in the center. And because of the way that the three-dimensional structure is, it's going to have some kind of rotation. Doesn't matter which direction. It's going to be in some random direction. It's going to be slightly over-rotating in one direction. So the whole cloud is, if it was spinning really, really slowly to begin with, as it collapses, it starts to spin faster and faster and faster and faster.
All right. This is a thing in physics known as conservation of angular momentum. And if something is spread out and it's got a little bit, even the tiniest little bit of rotation, if you draw all that stuff down and collapse it all down, the same total amount of rotation still has to be there. And what that ends up being is a much faster rotation as it squeezes down. And so when these things collapse, they spin much faster.
Yeah, and the famous example, of course, is the ice skater.
Yes.
If you see an ice skater doing a pirouette, and he's got her arms out, and they pull their arms in, and then they suddenly start spinning much faster.
Whipping around really, really fast.
Because when they had a larger radius, then they spun slower, and then when you pull it in, it becomes faster. And the extraordinary difference in that, the example for our solar system would be if we had a gas cloud that that it was originally spinning at a really gentle rate, like it took 1 million years to rotate this gas cloud. Once you collapse it down to the size of our sun, it's spinning at 0.6 of a second.
Wow. So when you're talking about these gas clouds needing a bit of a kick off in order to be able to collapse down, I mean, I'm now having this image of a very, very spread out gas cloud. How long does it take for a star to sort of collapse down and start turning on?
So that first initial collapse only takes about 100,000 years.
Again, I just love astronomers' sense of time and space. Only 100,000 years. But of course, that's a really short period of time.
Okay, that's not enough for the star to turn on, but it's enough to start forming a solar system as we might start to recognize a progenitor to the solar system. And what that means is that, our sun doesn't rotate at once every 0.6 seconds. That's clearly not the way that has happened. And the reason why that is because some of that angular momentum, instead of being all trapped inside the star, has actually gone into a disk structure. So whilst our sun sucked up 99.8% of all the mass in that original gas cloud, it actually only has less than 2% of the angular momentum in our solar system.
Wow. So it left behind a very small amount of material, which is, us and all the other planets and bits in the solar system. But we're all rotating really fast, or at least with a large amount of total momentum.
Yeah, and it's Jupiter and Saturn that really sucked up all that angular momentum. Yeah. They are big things and they orbit quite far away from the sun. So that's where most of that angular momentum for our solar system went.
The overachievers of the solar system.
Definitely, yeah. So we have this disk, and that's really important because that disk is now going to form all of our planets, pretty much kind of mostly where they lie today, which is really interesting.
Leaving aside the pretty much mostly, and let's just say formed all the planets where they are today and take that as a first order approximation, as it were.
Yep.
Looking at that snapshot at that point in time, it's collapsed down. We've got something which is sort of a prototype star in the middle and a big disk of material which the planets are going to be created from. Where do we go from there?
So this is where we can introduce a divide in our solar system where inside this divide, the rocky planets formed. And so Mercury, Venus, Earth and Mars are pretty much similar in terms of their compositions, their sizes. They kind of look the same, right? And then on the other side of that divide, you've got the four gas giants. You've got Jupiter, Saturn, Uranus and Neptune. We're not going to talk about anything else beyond that.
No, that's all not planet stuff. We're just talking planets today.
And that divide actually ends up being something really interesting, and that is called the snow line.
Snow line.
So the snow line. So imagine you've got your young star. It's not quite fusing yet, but it's still quite hot over in the center. So temperature falls the quicker you get away from, or the further you get away from that protostar. And the place where that temperature falls to where water can freeze, basically, is called the snow line.
That makes sense. Okay.
And that falls in between Mars and Jupiter. So there's a very different way that the planets form on either side of that snow line.
Okay, I think I'm going to need a little bit more help with that, though. Why do you get... Because there's a huge difference between a Mars and a Jupiter. They're so different. It's hard to imagine more different planets. Size, composition, the works. So how does that change give you such a big difference in planets? How does the snow line kick in like that?
Well, to shock you, actually, probably the planets formed in a very similar way to begin with. In fact, the physics is pretty much the same. And this is called the bottom-up model of planet formation. Bottom up because basically you start with lots of tiny things in your disk and you stick those tiny things together and you get bigger and bigger and bigger things until you get something that's the size of the planet.
Right. We've come across this concept a few times before. Little things clumping together, sticking together, and eventually gravity takes over and starts clumping them even more. But initially it's sort of electrostatic attraction, isn't it? Very, very tiny things, a little bit charged and clump together they go. And then that builds up, and eventually it's big enough that gravitationally they can start clumping together as well. And that's whether it's Mars or Jupiter, it's the same thing.
That's the same thing.
Okay.
What's interesting is that whole process happened much faster beyond the snow line because you've got ice out there. And it turns out that ice is really sticky. So you can stick the bits together much, much quicker when you've got ice and rocky particles to stick together. So the gas giant, or the cores of the gas giants at least, formed much, much faster than the terrestrial planets, or those rocky planets.
So why does that mean that the gas giants are giant and made of gas? Why does forming faster give you such a different kind of planet?
So, well, actually, the gas giants had a limit on how much time they had to form, which the terrestrial planets didn't have. So what happens is you can form your core very quickly, and of course for the giants that's now occurring much, much quicker. They're forming bigger lumps faster. And then the star does something interesting, which is it starts to turn on.
Right. So at this point, we don't yet have a bright sun in the middle of the solar system. We have quite a large lump of stuff, but it hasn't yet really turned on. It hasn't brightened up yet. It hasn't ignited.
It hasn't ignited yet, but it's got to the point where it's starting to get hot enough that the gas that's in the disk is starting to get pushed away from the star. So enough light is coming out to interact with the gas that's in the disk and push it further and further out. So that gas is being pushed out to the giants in the solar system, and we're just left with rocky things, basically, in the inner solar system.
Okay, so it's the radiation, the light that's coming from the very early sun, which is pushing stuff out towards the outer planets. What we now have as the gas giants. It's pushing it out, and they're collecting that gas.
And they're really, really big cores, so they can hold on to quite a lot of gas.
Oh, whereas the ones in the inner part of the solar system, the rocky planets, are having all of that stuff pushed away from them. So they remain quite small and lumps of rock.
Yeah.
Ah, okay.
So the gas giants actually have this time limit. They have to basically formed within 10 million years, probably even just a few million years from, say, T equals 0 when we started collapsing this cloud. And the rocky planets, however, they can just keep slowly accreting and adding bits of stuff for tens of millions of years.
So why that 10 million year time limit? Is that when the sun turns on?
Yeah, that's when it gets hot enough to start blowing the gas, basically, out to the outer solar system. So it's really now we start to get to another problem or interesting question, shall we say? Because now we're saying we've just got lumps of rock in a solar system, and we've just got gas and big core things in the outer solar system. Let's have a quick fast forward to what we have today.
Okay, let's check in.
So now if you were to take that planet Jupiter, say as it was at that point in time, and look at it today, it's fairly much the same. Okay. What that means is Jupiter's atmosphere is basically the first atmosphere that formed on Jupiter, and it's kind of held on to that. Now, lump of rock, however, that is going to become the Earth doesn't look like that now. Earth has this lovely atmosphere now, and most crucially, we've got quite a lot of water.
Yeah, that's a bit different, not expected. So where's
So
that
all the
come
water shouldn't be on Earth so far, according to our model, because we pushed all that water and it froze out and it became these icy giants.
So we're missing something.
So we're now going to have to think, okay, we've got to this point, we've got a lump of rock, we're going to have to put some water on it. But the water's all gone to the outer solar system.
So it's like we've got the base model of the solar system. We've got 4 rocky planets and we've got 4 big gaseous planets. Tick, well done. But now we're getting into the finer details, right? Earth isn't that. So where did all of that extra stuff come from? So now we've got to start adding in new parts to this model of solar system formation. Where did it come from?
Well, it has to have come back into the inner solar system at some
Right,
point.
okay.
Now, where it has come back in from has been sort of a big area of research for many decades. We thought maybe it came back in from the Kuiper Belt and from the Oort cloud, from comets. We know that comets are basically these dirty snowballs. When you bring them into the inner solar system, they melt and they've got some water on them, right?
That's what the tail is of the comet, isn't it? It's as they come in towards the sun, they warm up and they start just off-gassing all sorts of stuff behind them. And that's what we see as the tail of the comet. Is that right?
Yeah. So you could imagine that lots of comets may have hit the Earth over the history of the solar system. And so they just kind of deposited their ice on the Earth that became water and so on. And that's one of the reasons why we were really interested to go and visit a comet and look at the water and the ice that's on a comet and say, okay, does that look like the water and ice that we have on Earth?
Right. You could have a look at the chemical composition and ratios of different radioactive things and all sorts of stuff like that on Earth. And then if we got to actually sit on a comet and go, so what are you made of? Dig down into that. And if they're kind of similar, that does tend to point towards that as being the origin of many of the stuff that we see on Earth.
But it turns out that it's not.
Oh.
So
nice
we
idea.
sent a probe, right? We sent Rosetta. Rosetta did a wonderful job. Philae sort of did a good job. It tried really hard, didn't quite make it, but we still were able to measure very, very accurately the composition of the comet, and we measured the water, and it's not really the same as the water on Earth.
Huh. Okay. So it was a really nice theory. So I guess that could mean, all right, well, it wasn't from that comet, but presumably there was enough data for us to be able to, rule out comets as an origin entirely?
Pretty much. We think maybe only 5 or 6% of the Earth's water could have come from the Kuiper Belt or beyond.
Right. So what does that leave us with then?
Well, there's one other place in the solar system that does hold some water and probably held a lot more water in the past. Do you want to take a stab at where that might be?
I don't know. No, I've got nothing. Where?
So in the asteroid belt.
Okay.
So asteroid belt sort of straddles a little bit this snow line, right? And it probably, huge amounts of material, much, much more than there is today, used to be in the asteroid belt and used to have water in it.
This is in the space in between Mars and Jupiter, isn't it? Yeah. And so are you saying it's not a coincidence that it's on the snow line? Or it is a coincidence that it's on the snow line?
That's a very interesting question. It's probably related, but it's more related to the fact that Jupiter's sitting around there. Jupiter's the next big thing. So this is where we have to start talking about, okay, we formed things kind of in situ where they are today. But if we want to create the worlds that we see around us, the solar system we see, we're going to have to move some stuff around a little bit here. And this is where migration theory of the solar system comes in. So I'm going to mention 2 possible models, and they're sort of complementary as well as could be one or the other. But one really interesting one is we can start with is the Grand Tack model.
Grand Tack. Okay.
So the tack comes from the fact that like a sailboat tacking, because what this model is basically showing is that Jupiter may not have always lived where Jupiter is living today. Jupiter may have formed something like 3.5 astronomical units. This is the distance between Earth and the Sun. So 3.5 times as far away as we are from the Sun, which it's not where it is today.
Yeah, how many
So it's now at
units?
5.
Right.
So it might have started at 3.5, but it may have come in. It may have moved inwards after it was formed and kind of sucked up the material that was around it. That would have changed the gravitational dynamic of the disk, which meant that it could have lost some of that orbital motion and moved into the inner part of the solar system, maybe as close as 1.5 times as far away as we are from the sun.
Wow, so that's really close.
Really close, which is very, very interesting, because if you model that, Jupiter starts to bring with it in that migration a lot of ice and other things that were in from beyond the snow line.
And are we talking at a stage where Jupiter would have been as big as it is now?
Pretty much as big as it is today.
A really, really big thing.
Yeah.
Coming in quite close is going to really disrupt all sorts of things in the inner solar system.
Yeah, and drag a whole lot of stuff from the outer solar system in with it, including Saturn. So Saturn's now being dragged in as well. And now, interestingly, maybe Jupiter wouldn't have stopped. It would have just kept on coming in towards the sun. But actually, Saturn comes to the rescue here, because Saturn may have entered an orbital resonance with Jupiter, which means that every 2 times that Jupiter went around the sun, Saturn went around 3 times. Exactly.
Right. So there's some really interesting gravitational dynamics going on at this point. These huge objects coming into basically where we are in the inner solar system and messing everything up. But at the same time, Jupiter and Saturn are getting involved in this little gravitational dance. And what does that do? Does that drag them back out again?
So Saturn kind of then holds on to Jupiter, and eventually there's a loss of energy, and they they get dragged back out to the outer solar system to where they are today.
That's very cool.
It's very, very cool.
But as you said, when Jupiter came in, it dragged a whole bunch of stuff along with it. And so I'm going to make a guess here. Some of that stuff was ice.
Ice, yep. Which then came to Earth, became the water that we have on Earth.
So Earth, the very early rocky Earth, got absolutely bombarded by bits of stuff that had been dragged into the inner solar system by Jupiter on its grand tack across the solar system.
Exactly, yeah.
Got its oceans and its atmosphere, and then Jupiter and Saturn went, oh, my bad, sorry, and wandered back out. And here we are with this planet covered in stuff.
Yeah, a cool supporting piece of evidence for this theory is Mars, actually. Because you think, if we got in trouble from Jupiter wandering in...
Surely it wasn't just us.
It wasn't just us. Mars got in an awful lot of trouble because of this.
Yeah, so you should be able to look at Mars and see similar kinds of evidence. Mars isn't covered in oceans.
No, it's not. But what's interesting about Mars is that Mars should be bigger. Mars should be about the size of the Earth.
When you say it should be, why should it be?
So there was enough material in the disk where Mars is now for it to be at least as big as the Earth.
Right. But it's not. It's a third?
Yeah, it's tiny.
Yeah.
So
what happened?
Some of that stuff maybe when Mars was forming and this Jupiter migrated in, it kind of dropped material, pushed it away out of Mars's orbit. So Mars wasn't able to become as big as it should have been.
Well, I mean, given that Mars is between us and Jupiter during this great migration of these enormous planets, you'd kind of think Mars probably actually copped the brunt of that even more than Earth did.
Exactly. Yeah.
So while Earth managed to pick up, thanks very much, we've now got, water and clouds and stuff. Mars went, oh yeah, thanks for that. I've now had, 2/3 of my material stripped off me. Thanks, tar.
Yeah. So it's not the only way you can create a small Mars, but it's a good piece of supporting evidence for the Grand Tack model as well. So that's really quite interesting. But it's not the only way we think that this could have happened. There is a kind of a alternate / complementary theory, depending on how you put the two together.
Well, before we get onto that, how strong is the evidence for this? What did you call it? Grand Tack theory. How strong is the evidence for Jupiter and Saturn wandering their way into the inner solar system in the way that you described?
Well, we have pretty strong evidence that planets have to migrate. We know this because we've seen planets the size of Jupiter orbiting their host stars within the orbits of a Mercury equivalent. And you just can't form a Jupiter-sized planet at that distance from a star.
Right.
It can't do it.
So we look at other systems, exoplanet systems and we see these enormous planets in places where, well, they didn't form there, but we've seen quite a few of those, is what you're saying.
Yeah.
And so this kind of migration, it's got to be fairly common.
It was a huge shock when we first started looking at these exoplanets, and we found these hot Jupiters, and we found quite a lot of hot Jupiters. You might expect to find the odd one if you think, okay, maybe something went wrong in that solar system and it kind of pushed, billiard balls pushing things
that
around.
That one's a bit weird, but there you go. But no, this is fairly regular.
Yeah, and much, much more regular than you might expect if it was just kind of a random sequence of events.
So the notion of planets forming and then staying where they form, and that just being the way the solar system is, or the way a solar system is, that's actually not normal at all. That you'd actually find things moving around all over the place as the whole system evolves.
Yeah, particularly the gas giants. They seem to be the most mobile.
Because they're bigger?
Because, they're more gravitational influences from them and to other gas giants as well.
Okay. But getting back to, you said the next theory, the other theory.
Yeah. So the other one is called the Nice model, which is kind of, it comes from the Nice, which is the city in France where the team working on this were developing this. And this is a similar but different way to look at migration. So in this example, we have in the first 500 million years of the solar system. So all this stuff's really early, right? It happened a long time ago. Again, you've got Jupiter and Saturn moving around. In this case, Jupiter and Saturn moved into such a position that they also formed a resonance. So this time it was Jupiter going around the sun 2 times for every 1 time that Saturn went around.
Okay.
And this also creates a whole lot of dynamical instability in the solar system, and it starts flinging stuff everywhere. You see the computer simulations of this, and it's amazing. You can just throw objects all the way around the.
So Jupiter and Saturn come in and causing havoc,
causing
basically just going nuts,
utter havoc. And we think this is one reason, for example, that Uranus and Neptune got pushed out, because they should have formed a bit closer to Saturn and Jupiter. But they seem to have been pushed out. And there's even some ideas that maybe they changed places during this time. So poor old Uranus may have used to be the furthest planet from the sun, but then Neptune kind of took over. And, well, maybe there was even another gas giant, icy giant out there that has been kicked out of the solar system entirely. So really weird and wonderful stuff. But part of this is that if you achieve this resonance, then you start to throw things from the outer parts of the solar system in towards the center again. And this is another way to put the water back into the inner parts of the solar system. It doesn't necessarily have to be as far out as the Kuiper belt, but even the stuff in the asteroid belt and kind of things that were around about where the giant planets are now, all those ices could have been thrown in at this point.
So under this model, Jupiter and Saturn didn't wander their way into where we are, into the inner solar system, but they did crazy stuff more out in the outer solar system. They got into these crazy resonances and started flinging stuff around in all sorts of different directions. And a lot of that ended up in our part of the world, or our part of the solar system, and collided with us and gave us our water and our other stuff in that way.
Yeah, which is also very interesting. And also there are ways, okay, you can also explain, for example, why Mars is a bit smaller using the same gravitational dynamics. So we have some really interesting migratory models now for our own solar system, which I find quite surprising, actually. I like these models. It tells us something interesting about how our solar system maybe or didn't always look like it looks now.
So it sounds like, from what you're saying, it sounds like, as you said a while ago, right? Let's look at what we've got now. How can we reverse engineer that? How could we have got to where we are? And there's a bunch of things that we have to explain. But it doesn't sound like we have a definitive answer. It doesn't sound like, well, to 3 decimal places, this is what happened. We have a few models which, if you run those, for example, as a simulation, then they would give a solar system with roughly the right kind of dynamics and flinging stuff around which could make our oceans and that sort of thing. But there's a few different ways that you could do that. So we've got a couple of good, compelling, competing models. Is there ever going to be a way to decide between these? Or is it going to be a matter of, well, let's see what's happening in other parts of the universe and maybe we can cross off one of those possibilities, or maybe one of them gets a bit more support, but maybe we'll never know.
So this is, I think, where exoplanet science has done such wonders for solar system science, because we've been able to look at all these other systems and we suddenly have lots of endpoints that we have to explain. And the physics that we can use is exactly the same. We can't use different physics.
Yeah,
in
we're not allowed to
different
bring in
solar
new
systems.
rules.
No. So we have to, if we have a model or a system that works in our solar system, then we have to be able to use something similar to explain what's going on in other systems. And that's really interesting, and it's something that's very new. And even with the new, so we had these hot Jupiters, these very, very big planets orbiting close to the host stars. We've now got a new challenge to explain, which are called Hoptunes.
Hoptunes?
Hoptunes.
Hang on, that's a hot Neptune.
It's a hot Neptune.
So you've got hot Jupiters, but they didn't call them Hoopiters. But
I think we got more creative.
The temptation with a hot Neptune must, hang on, we could call them Hoptunes. Fantastic.
Hoptunes. So we've got Hoptunes now. So how do you pull something the size of Neptune in to be as close as it is to the sun through migration? And through using those systems and getting even better observations of our solar system around us today as well, we can start to really add to our models and start to draw lines through the ones that just don't work and produce the effects that we have today.
I mean, the models have got to be able to account for a whole bunch of different scenarios anyway. There isn't only one kind of solar system or one kind of planetary system. There's going to be lots of different initial conditions and, you know, systems forming in all sorts of different ways. But ultimately, it does come back to the same physics and the same kinds of dynamics that these things will be formed from. And so ultimately, with enough data, you should be able to come up with a fairly small set of models that would be able to explain most of the stuff you see.
Which is pretty amazing, considering we're sitting here 4.5 billion years later, and we're able to now go back to the very earliest stages of our solar system and say, well, you know, maybe this happened or maybe that happened. And I think that's one of the wonderful things about and unexpected things you can do with science is talk about areas and times in the universe that you were totally inaccessible to you before.
Well, that brings us to the end of another edition of Syzygy. Listen, there's a number of different ways, if you want to, that you can get in touch with us here on the show. All sorts of different ways, in fact. We're all over social media. Emily, tell us a bit about Syzygy's social media. Where can people find us out there on the web?
Well, if you need your social media short and fast and punchy, then you've got to go to Twitter.
Indeed. So where are we on Twitter?
We are at SyzygyPod, SYZYGYPOD, and you can find us there. We're talking about episodes when they're released, things that are relating to upcoming episodes, all sorts of wonderful things that kind of trigger our sense of humour across the interwebs.
Yeah, I mean, sharing little bits, little snippets of astronomical news and interesting things, and linking to people who are just doing interesting stuff in the world of astronomy. So that's Twitter. We're on Facebook as well, facebook.com/SyzygyPod. Just go and find us. We post all of the episodes up on Facebook as well. And if you want to send us a message or a question or a query or a comment through Twitter, through Facebook, you never know. We might even feature it in an upcoming episode. We've done that a couple of times now, and we're always interested in hearing from you. The other way you can do it, of course, is go to our webpage, syzygy.fm, and you can go to the contact part of the page there and just send us a little note in that way. That's the other way that you can do it. If you enjoy the show and you want to help us, a couple of ways you can do that. First of all, we'd love you to leave us a review. Give us some stars, because the only way that people can find us in the world of podcasting is generally by searching for us. But the searches work much better when there are reviews out there on things like iTunes and the other podcast catchers. So if you're enjoying the show, leave us a review. Give us some stars. Tell the world what you think. We'd really, really appreciate that. If you really enjoy the show, there's one other way that you can help us out as well, and that's by going to our Patreon page, patreon.com/SyzygyPod. That's a way that you can become a patron of the show. If enough people become patrons of the show and give us $1 a month, $1 an episode, something like that, then that gives us the opportunity to be able to spend more time doing what we love doing and actually creating these highest possible quality podcasts and be able to do all sorts of big and interesting things. So if you enjoy the show, we'd love you to become a patron. But otherwise, just tell your friends, tell your family, talk it up, and give us the support in that way. Otherwise, we'll catch up with you next time on Syzygy.
See you next time.
Bye-bye.
I'm getting used to this production business.
I'm glad someone's paying attention.
Well, this is my third coffee.
I'm wired. I can't even blink.
One day you're going to take all those random clips like that one and just mesh them together into something that just doesn't make any sense.
Have you not been listening to the end of the show?
Yeah.